Thank you very much, John. Good evening, ladies and gentlemen. Thank you for coming out tonight. Normally, if you've come to hear someone talk about aviation and climate, it's going to be the sort of talk that makes you feel very guilty about all of the flying that you do and all of the carbon dioxide that comes from planes and causes climate change. But that's not my topic tonight. I'm going to turn that question on its head and think not about the contribution of aviation to climate change, but rather to think about how climate change might be impacting on aviation in several different ways, as I'll explain. My slides are all in the public domain. Feel free to obviously take notes and pictures if you want, and if you happen to be on Twitter, that's where you can find me. So let me just explain and unpack in a little bit more detail what I mean about the two-way interaction between aviation and climate. We've known for many decades that aviation, of course, involves burning fossil fuels essentially, and that puts carbon dioxide into the atmosphere, which causes the climate to change. Just out of interest, does anyone know what percentage of global carbon dioxide emissions currently comes from aviation? Anyone like to hazard a guess?
2%.
So I'm hearing 2%, 3%, did I hear 10%? 10%? Any more offers? Fraction of a percent. Okay, we've got everything under the sun there. Well, that's interesting because I normally get responses like 20 or 30%, and I think the environmental movement's done a very good job of persuading us that aviation is more damaging than it is. It is 2%, so well done whoever said 2%. 2% globally. Of course, the distribution around the world is not equal, and it's more like 6% in the UK. There's a relatively minor contribution then to climate change, and actually the proper thing to do is to look at the accumulated emissions per sector since the start of the Industrial Revolution, because that's what's driving the climate to change, not today's current annual emission rate, but to look at the accumulated emissions over time. And because aviation is a relatively recent way of burning fossil fuels, it's only been around for about 5 decades, and we've been burning fossil fuels for all sorts of other reasons to power the Industrial Revolution a century and a half ago. Aviation's contribution to climate change is at the 1% level. Anyway, there have been many academic studies on this, and it's not just carbon dioxide, but all of the other particulates that come from aviation, actually a lot of water vapour as well, and that can turn into things called contrails, which can develop into clouds. There's a whole host of different ways in which aviation causes the climate to change. But I'm going to talk about this reverse arrow, how the changing climate might affect aviation. This is a very new research topic. There are dozens of possible ways that climate change might affect aviation. We know very little about most of those mechanisms, and I'm going to focus tonight on 5 possible ways that have been studied, and so we can put some numbers and I can give you kind of predictions, if you like, about how flying later this century might be different as the climate changes. And just very briefly, I'll flash up this proceedings of a conference that was held about 6 months ago in Toulouse that I attended, and just to show the importance of what I'm talking about. I won't read through the entire recommendations, but you can see this one, that a changing climate scenario might render some of today's aerodrome, airspace and airframe design and operation standards inadequate in the years or decades to come. Using past climatological records alone as an indicator of future climate at an airport may be insufficient. In other words, the past is no longer a guide to the future in a changing climate, and as this very influential group of academics suggest, some of today's airplanes and airspace in airports might be rendered inadequate. In other words, might not be able to cope with the climate change that we expect to happen. This is an infographic that summarises the 5 possible impacts I'll talk about tonight. It's taken from a report I co-authored for the United Nations Aviation Agency in 2016. Let's go through these possible impacts in the order that you would encounter them if you were taking a flight tomorrow, for example. Well, the first possible impact is that we know that the sea level is rising and that a lot of people live near the sea. There's a statistic that I think 50% of the world's population lives within of the order of 100 miles of the coast. We like to live near the sea, and of course airports tend to be located where people are located. That makes sense. And so lots of airports, lots of the world's largest airports are coastal airports, and because the sea level is rising and storm surges might well be expected to intensify because of climate change, we might see more flooding at coastal airports. I'll go through each of these impacts in more detail shortly. This is just to introduce them. Well, let's suppose the airport's not flooded. The next possible thing climate change could do to your flight is make it harder for the plane to take off. For every 3 degrees Celsius rise in air temperature, the density of the air decreases by 1%. And that means that the lift force that gets the plane off the ground is also reduced by 1%. And so we have evidence, which I'll show you shortly, that planes are already finding it harder to take off because of the global warming that has occurred so far. And we expect this effect to intensify going forward. But let's suppose your plane does manage to take off. The next possible thing that could go wrong and be made worse by climate change is the simple fact that we expect more extreme weather. For every 1 degree Celsius rise in temperature, the atmosphere can hold 7% more moisture, more humidity, and moisture is a kind of an energy source for weather systems, so we generally expect more disruptive weather, more thunderstorms, for example, because of climate change. And a plane being struck by lightning is a very serious event, as I'll show you shortly. Another possible thing that could happen is that the wind patterns at flight cruising levels are changing because of climate change. Moving around, they're getting stronger, and that could have impacts as well on journey times and flight routes. And then the thing that I've personally been researching is the possibility that the atmosphere could become more turbulent. And I'm sure anyone who's flown will have flown through a patch of turbulence and been buffeted up and down randomly and been told to sit down and put your seatbelt on urgently because of the possibility of very strong turbulence kind of catapulting you around inside the cabin, and that does happen. So I'll spend actually quite a lot of my talk focusing on that possibility, the possibility of more turbulence in the future and the consequences that could have for aviation. Okay, so let's go into these 5 impacts which have been studied, and I'll show you what the science is, and the physical mechanisms behind the changes, and I'll try and put some numbers to each of these impacts to give you an idea of how bad things could be, worsened by climate change. Well, we know from satellites that the sea level is rising in a global average sense by about 3.5 centimetres per decade, but the rate of rise is accelerating, so if you come back in a decade's time, it will almost certainly be more than 3.4 centimetres per decade. Sea level is rising partly because of melting ice, but also a very important effect that's often forgotten is the fact that the oceans expand when they get warmer, thermal expansion. As you warm water up, it expands, and because it can't go sideways and it can't go down in the ocean, it's got to go up, so the sea level rises as a consequence. Now, many airports around the world don't have to worry about this. These are the airport codes for Gatwick, for example, which is 62 metres above sea level. Heathrow is 25 metres above sea level, so Gatwick and Heathrow are not too worried about rising sea levels. But many large international passenger airports are only a few feet or a few metres above sea level. LaGuardia in New York is 6 metres above sea level. Dundee is 5 metres. San Francisco International Airport is 4 metres above sea level. John F. Kennedy in New York, 4 metres above, etc., etc. Some airports are actually below sea level. Famously, Schiphol in Amsterdam is 3 metres below sea level and obviously has some very good flood defences in place. The lowest large passenger airport in the world that I can find is 22 metres below sea level in Kazakhstan. Now, people have studied the effects of rising sea level on airport operations, and a study here concluded that 13 of the USA's largest airports have at least one runway within reach of a moderate to high storm surge. That's currently, and of course sea level rise only adds to this effect. And on the other side of the Atlantic, a European study found that sea level rise could threaten runway capacity at more than 30 European airports. And this is not an impact of climate change on aviation that is confined to the distant future. I'm not talking about impacts decades from now, but we see airport flooding today, possibly exacerbated by climate change. In 2012, many of you will remember Hurricane Sandy in the Atlantic Ocean, which made landfall and then moved north up the North American coast on the east coast, and eventually, of course, no longer was a hurricane, but it was called a superstorm, at least in the media. Anyway, a very stormy storm, which brought a storm surge with it, so a pile of water underneath the storm kind of being sucked along. That indeed flooded LaGuardia Airport in New York. Both of the runways and all of the tarmac and concrete was underwater. The airport was shut for a few days in 2012. And of course, climate change and rising sea levels is expected to make events like this happen more frequently in future. There was an academic study published recently which said that a storm as bad as Sandy will happen once every 5 years in New York by the middle of this century. So a storm of this magnitude, bad enough to close the airport for a few days. We're expecting to see that happening every 5 years in a few decades' time. It doesn't happen every 5 years now. Well, this little animation here just shows you how much of LaGuardia Airport and JFK, John F. Kennedy Airport, disappear underwater for various sea level rises. And we're expecting something like, well, a few feet, not this century, but on a time scale of a few centuries. This is Hong Kong International Airport. They're currently building a third runway. There are 2 runways currently, as you can see. It's a 2-runway airport, but they're building a third runway, and they're building into the designs the consequences of climate change and sea level rise, because they know that it's going to be a problem in the lifetime of this airport. So they're including in their plans 13.4 kilometres of a seawall to help protect the airport, and especially the third runway, from flooding and storm surges, which they expect to get worse in the lifetime of the airport because of sea level rise. So there's an example of academic thinking and climate change feeding into decision making today in respect of airport operations. I mentioned takeoff weight restrictions. Yes, so cold air, in simple terms, well, it's heavier. So there's more air molecules in a given centimetre cubed. When the air warms up, there are fewer air molecules, and that pushes up less strongly on the wings of the plane. So the warmer the atmosphere, the harder it is for a plane to take off. Because the simple equation for a plane to take off is that the lift force has to be stronger than the weight of the plane, which is gravity pulling it down. So as you warm up the atmosphere, you reduce the lift force because the atmosphere is becoming thinner. The number of air molecules per meter cubed is less. And so they're pushing up less strongly on the wings of the plane. And there's a possibility, well, it's not just a theoretical possibility, it's already happening. The global warming that has happened so far has made it harder for planes to take off. And indeed, in some parts of the country, like the Middle East, it's the current policy to schedule long-haul departures for the morning and the evening, but to avoid takeoff in the middle of the day when it's hottest, precisely for this reason. The warm air makes it very difficult for planes to take off. Academics have studied this, so here's a paper, well, a series of papers actually, that have been published in the past few years, looking at different airports. I'm showing you here, for no particular reason, Washington Reagan National Airport. So in both of these charts, we go from 1980 to the present day in blue, using observations, and then extrapolating forward in time using climate projections to the 2070s. What's being plotted here is the number of days a year when the maximum takeoff weight of a Boeing 737 has to be reduced by £10,000 or £15,000 because it's too hot for the plane to take off. So this already happens on something like 50 days a year at Washington Reagan Airport, and I've heard of people who've been bumped off planes because it's too heavy for the plane to take off. What can you do? You either remove luggage or passengers or fuel to reduce the weight of the plane. So it already is happening that people are being bumped off planes because they're weighing down the plane too much and it can't take off. And we've seen an increase since the 1980s in this phenomenon in line with global warming, and the projection going forward towards the end of this century is that we'll see a 50 to 200% increase in the number of days a year at this particular American airport where the Boeing 737 will have to have its maximum takeoff weight reduced. So again, this is something that's arguably already happening. We've already seen an increase in the number of days a year when a medium-sized plane is too heavy to take off because the atmosphere is too warm.
Could I suggest something?
Of course.
The high altitude airports also have difficulty, and sometimes you can't actually fly into the airport because of this effect at high altitude. So it isn't just, it's more restricted at high altitude, isn't it?
Yes, the key factors are the altitude of the airport, because as you rightly say, the higher up you go in the atmosphere, the less densities. So in effect, going up in the atmosphere is a little bit like warming the atmosphere up. It has the same consequence for density. The other thing that matters is the length of the runway. It's at airports with short runways because the speed of the plane comes into the formula for the lift force as well. So the altitude, it tends to be a problem at high altitude airports with short runways in summer. Those are the three factors that matter. Thanks for the question. I mentioned more extreme weather. On average, a plane is struck by lightning once a year, annually, currently, I beg your pardon. So once every 12 months, every large commercial plane that's in service is struck by lightning. It's a major impact, of course. The plane has to be taken out of service and inspected and maintained and repaired. This, by the way, is from the 1980s. This is a NASA research plane that was deliberately flown into thunderstorms, believe it or not, to test the response of the plane to being struck by lightning. So this plane was struck by lightning, I think, many hundreds of times over its lifetime, just to see how a plane responds when it's struck by lightning. Now we have, without going into too much detail into the numbers in the background, we have a general expectation that there will be more lightning strikes in future just because of climate change putting more energy into the atmosphere, more water vapour. And so, if you want to dig down into the details, what these numbers show for lots of different climate model simulations is the percentage increase in the number of lightning strikes for every 1 degree Celsius in global warming. So quite a spread of different results from one model to the other. Some models only show a 3.4% increase in lightning strikes per degree Celsius. Some models show 17%. But the average across all of these models is about 12%. So we expect 12% more lightning strikes in the atmosphere per degree Celsius of global warming. And because we expect a few degrees Celsius of global warming by the end of this century, we can add up a few multiples of 12%, and we expect something like 50% more lightning strikes. So lightning strikes becoming 50% more frequent by the end of this century. And of course that means that the average plane can expect to be struck by lightning about once every 8 months rather than once every 12 months. And again, that might have operational consequences in terms of taking the plane out of service to be repaired. But now I'll get on to the kind of things that I've been looking at in my own personal research, because all of that's been done by groups in the US and elsewhere. I'm going to talk about how the jet stream might change because of climate change, and in fact arguably already is changing because of climate change, and the impacts that the jet stream might have on aviation in the future. Here is a NASA satellite movie of 1 month's worth of Northern Hemisphere jet stream. So here we are looking down over the North Pole, and we're about to zoom into North America. This is a NASA image. This is the jet stream. We're up at about 35,000 feet here, where planes tend to fly. And as you can see, it blows from west to east in the middle latitudes. Can reach speeds of 250 miles an hour. The red colours here are the faster speeds, obviously. Goes all the way around the world, and there's another one in the southern hemisphere too. I'm going to focus on the northern hemispheric jet stream. Blows from west to east, and as you can see, normally it blows from west to east, but it does develop these waves in it that are called Rossby waves. And that they have a crucial impact on our weather. It's a very interesting research topic that I'm not going to touch on today. I'm interested in the impacts of this jet stream on flights, because obviously an eastbound flight from New York to London is going to want to try to get into this jet stream and boost its ground speed, because if you can get into a 200 mile an hour wind, you're going to reach London a lot quicker. And the converse is true for the reverse journey. If you're flying westbound from London to New York, you're going to want to get as far away from this jet stream as you can, because it's going to be slowing you down with the headwinds. So I'm interested in how the jet stream might be changing because of climate change and the impacts that that might have on journey times and flight routing and also turbulence. Now, we have evidence that the jet stream is speeding up because of climate change. And we understand the reasons why, and I don't really want to go into it tonight. It's in terms of the temperature gradient between the low latitudes and the high latitudes. Anyway, we have a good physical understanding of why the jet stream ought to speed up because of climate change. We see it speeding up in computer models, and we also see it speeding up in this chart in essentially satellite observations. So the left chart here shows over the North Atlantic, so here's North America and Europe, Greenland, Iceland. This chart shows in colours, in metres per second, going up to 45 metres per second, the average strength of the jet stream a few decades ago. Okay, so it gets kind of quite strong over North America, and it tends to weaken off over the North Atlantic and get relatively weak by the time it reaches Europe. The panel on the right shows the way the jet stream has changed, has strengthened over the past few decades. So this is a kind of basic state for the jet stream, and this is the change in the jet stream. So you can see it's got about 5 metres per second stronger, and it was only about 40 or 45 metres per second strong in the first place. So that's about a 10% strengthening in the jet stream. And that has consequences for journey times and flight routes, and also for turbulence, because there's 3 times more of a special kind of turbulence called clear air turbulence. I'll come on to that. There's 3 times more turbulence in the jet stream than there is outside the jet stream. The jet stream is where most of the turbulence is. So if the jet stream is getting stronger, then we expect turbulence to get stronger as well. And I'll go into that in more detail shortly. There's a bit of audience participation in this slide, so forgive me for asking for a show of hands shortly. I'm going to think about how flight routes affect journey times, because it's not obvious at all. And there's a very subtle mathematical effect. Let's suppose you've got to get from New York to London and back again. So you're going to do a round trip across the Atlantic and back. Let's suppose the plane flies at 500 miles an hour. I'm just making that number up really, it's about right. I'm just trying to prove a point here. The numbers don't matter too much. Well, obviously, if there's no wind in the atmosphere, if there's no jet stream, what is the plane's... Well, it's not. I'm not even going to ask the question. It's so trivial. Obviously, the plane's eastbound ground speed is 500 miles an hour, and the westbound ground speed is 500 miles an hour. And so the average ground speed for the round trip is 500 miles an hour. I hope that's transparently obvious. But now let me put in a jet stream blowing from New York to London at 100 miles an hour. Okay, so now we do have a jet stream and we do have winds blowing. Now what is the ground speed for the eastern leg of the journey? 600 miles an hour, thank you, yes. It's going at 500 relative to the air, but the air is moving at 100 relative to the ground, and so you just add the two together with a 100 mile an hour tailwind. And what about the westbound ground speed? 400 miles an hour, thank you, very good. So now what about the average ground speed for the round trip? 500? Anyone think anything different from 500?
480.
Ah, well done. It is in fact 480. It's not at all obvious when you... So you'd think that the eastbound journey would get 10 minutes quicker and the westbound journey would get 10 minutes longer, and that they would all cancel out and that the average would be the same. But that's not what happens when you do it on the back of an envelope. You can't just take 600 and 400 and add them together and divide by 2. That's the wrong kind of average to take. In mathematical parlance, we want to take the harmonic mean rather than the arithmetic mean. That's how Pythagoras would have put it. What you actually have to do is multiply the two numbers together and then divide by 500. That's the right calculation to do. And if I had a blackboard, I might go through that, but it's a trivial calculation on the back of an envelope. It comes out to be 480 miles an hour. In other words, the two changes do not cancel each other out. The average speed of the plane is slowed down by the jet stream. And I once was asked why, to explain this effect live on Radio 5, and it's a bit tricky, but essentially what's happening is the plane is spending longer in the parts of the journey where it's not moving very fast. That's the best explanation I've been able to come up with without going through the equation. So the westbound journey contributes more to the average than the eastbound, and as it slows down, it spends even more in the slow part of the journey, so that there's a kind of weighting to that part of the journey compared to the eastbound. Still can't explain it very well. Anyway, what it means is that if the jet stream is speeding up, then this effect is going to become even more pronounced, and the average speed will be reduced even more. So journeys will get longer, and we've studied that. There's no exam at the end of my talk, so don't worry about these equations, but as I said, this was a kind of proof of concept. I want to do a proper job, so I'm going to use the flight routing equations. Every time you board a long-haul flight across the Atlantic, for example, someone, a mathematician somewhere, will have solved these equations to calculate the best route to take. You would think you would just go along the shortest distance route. So you'd get out a globe, you'd draw a line. Wouldn't be a straight line, because it would be along the surface of the sphere, but you'd connect London and New York with what we call the Great Circle, which is the spherical equivalent of a straight line. And you think you just fly along that because it's the shortest distance, but that's not what flights do, because they don't want to minimise the distance, they want to minimise the time, because that minimises the fuel, which minimises the cost. And it turns out it's beneficial to fly away from the Great Circle, and you'll cover a greater distance in the journey, but if the jet stream is behind you pushing you along, that effect will more than compensate and you'll arrive earlier. So you covered a greater distance, but you've done it in a shorter time because the jet stream has helped speed you up. And these equations solve that mathematical problem and tell you what route to take that minimises the fuel burn. And it's worth the airline solving these equations. They have to pay a mathematician, I don't know, $100,000 a year or something, but they more than make back that money in fuel savings from solving these equations very accurately. So no one realises this, but every time you board a plane, these equations have been solved to figure out what route to take to get you to your arrival airport as soon as possible, burning the least amount of fuel. So what I've done is I've taken some wind patterns from an atmospheric model, because of course we don't have satellite observations of the future, so we have to use computer simulations. What you can see here, the white arrows are the jet stream. You can see it blowing around. It goes north and south, and you see those Rossby waves I mentioned. And the black line is the best route from New York to London in that particular wind pattern. So it does vary a lot. As the jet stream moves north, you'll see the black line move north as well to get into the tailwinds. If I showed you the westbound route, it would be very different because it would try and get away from the jet stream, whereas the eastbound flights try to get into the jet stream. I think a lot of people think that if you take 100 flights from New York to London, it's always going over the same part of the ocean, but it's not. The flight route depends very sensitively on the wind pattern. What I've done is I've looked at the journey times in these computer simulations for eastbound and westbound, and they're just plotted here in these histograms. But without going into too much of the mathematical detail, we do indeed see that when we turn up the amount of carbon dioxide in these simulations, as the jet stream gets stronger, the eastbound journeys get shorter, which makes sense, we expect them to. They're getting a stronger tailwind, and that's getting them across the Atlantic to Europe in less time. And as with many things in climate, it's the extremes that change the most. So the probability of a very rapid eastbound crossing later this century, I calculate, is going to more than double. So we're going to see a lot of early arrivals of transatlantic planes into Europe because they've been pushed along by a very strong jet stream. Actually, that's a bit of a problem for the airlines because if you're meant to arrive, you're not allowed to arrive into Heathrow too early in the morning because of noise problems. So in fact, I think I've been on a transatlantic flight that was pushed along by a very strong jet stream and arrived in London before it was allowed to land, and the problem is you just have to fly around in a big circle and wait until 6:30 when you're allowed to land, and then you come in. So airlines actually aren't too happy about arriving too early if it's early in the morning and they're not allowed to land. And conversely, westbound journeys in this study get longer, as you expect. And again, the probability of a very long westbound flight between London and New York kind of doubling. So I think we might see a lot of delayed arrivals unless the airlines change their schedules and factor this effect in. I think we'll see delayed arrivals into North America. My university, all universities, I believe, pay media monitoring companies to check for mentions of that university's name in the media anywhere in the world. This is part of reputation management. If someone says bad things about my university on a Chinese or a German TV channel, we want to know about it so that we can correct the facts. And so all large organisations pay, I think, the same company to monitor. So every time on any TV channel anywhere in the world, any radio channel, any newspaper, any magazine, we get an alert whenever University of Reading's name is mentioned. One day we got an alert to say that we'd been mentioned on this primetime German quiz show, the Weisden, a very popular, on the equivalent of BBC One at 7 o'clock in the evening, a bit like Who Wants to Be a Millionaire, a very popular quiz. And we'd been mentioned on it, and obviously our first thought was that the algorithm has made a mistake here. There's no way we would have been mentioned on this quiz show, but we were. There was a question. I don't know I'm sure someone speaks better German than I do, but I think essentially the quizmaster is asking which of the following will soon be a consequence of climate change. Option A, submarines going deeper in the Pacific Ocean. Option B, transatlantic flights taking longer. And option C, container ships more quickly crossing the Mediterranean, I think. Anyone speak German? Anyway, as you can see, the contestant chose option A, and they lost all their money, sadly. I show this to my students. It does pay to read my papers in a pub quiz. Anyway, I digress. Have these changes already begun? Well, of course, it's too early to say, but I keep a very close eye on the jet stream. It's the first thing I do when I get into the office every morning is I have a look at the jet stream across the Atlantic. There are public websites where you can do this, and I always do it, especially before I board a plane. There was a 5-day period 3.5 years ago where the jet stream was blowing very quickly, 250 miles an hour. I was astonished, really. And consequently, in this 5-day period, the record was broken for the fastest transatlantic non-Concorde crossing. A British Airways flight crossed in only 5 hours and 16 minutes. And actually, I must update my slides because earlier this year, that record was itself broken. A further 3 minutes were shaved off, and the Norwegian plane crossed in 5 hours and 13 minutes. I think we're going to continue to see this transatlantic crossing time record broken in the future, in coming years and decades, as the jet stream continues to speed up. I think we'll see more minutes shaved off this flight time. A journalist once asked me, will we see a sub-5-hour flight? And, well, not for a long time, I think, but I think we will see incrementally 2-3 minutes keep being shaved off this record, and eventually maybe we will see a sub-5-hour flight in our lifetimes, I don't know. Consequently, or conversely I should say, in the same 5-day period, some flights took off from Heathrow with what should have been enough fuel to make it all the way to New York, but the journey was taking so long because the headwinds were so strong that they realised they weren't going to safely make it to New York, so they had to stop in Maine to make an unscheduled refuelling stop. And again, I think we'll see more of this happening in future, and there's a limit to how much fuel a plane can carry. And I know people to whom this has happened, crossing from the east coast to the west coast of the US. But here it's a transatlantic crossing that the journey was taking so long because the headwinds were so strong that it wasn't safely going to make it to JFK Airport and had to stop to refuel. I think we might see more of this happening in future too. And I'll finish by talking about turbulence, which is personally the thing I've become famous for. I'm known for, and as a scientist now, is this prediction that turbulence will get more severe in future. Of course, turbulence is everywhere. It's in your bathtub, it's in your cup of coffee. Fluids generally are, if you smoke a cigarette, the smoke is turbulent. Turbulence is everywhere. Of course, it's in the atmosphere and the ocean. And famously, it was painted by Vincent van Gogh in a series of paintings. So here's his, I think that's Dutch for the Starry Night from 1889. So here's his depiction of atmospheric turbulence. And actually, this is very scientifically accurate. In fact, I think I've got the slide here. Yes, a team of academics have studied the turbulence in his paintings. This is a bit of a digression, but an interesting one. Because turbulence has specific mathematical properties. For example, it has a minus 5/3 energy spectrum, if you want to know the technical details. So there's a specific mathematical property that turbulence has. And so these academics studied whether the turbulence in Vincent van Gogh's paintings captures that mathematical law accurately. And it turns out, well, to summarise a complicated study, it turns out that the paintings of turbulence he did when he was in a period of prolonged psychotic agitation, as the abstract of the paper says, basically when he was in a very depressed state, those paintings do correctly capture the mathematical properties of turbulence. The paintings of turbulence he did when he was in a good mood, he gets the mathematical properties completely wrong. So this has led people to say that you've got to be mad to understand turbulence. You've got to be insane to understand turbulence. And as someone who thinks he understands turbulence, I have to, well, anyway, no comment. Turbulence is a major problem for the airlines. There are tens of thousands of encounters with moderate turbulence and thousands of encounters with severe turbulence annually in the USA. And by the way, there's a particular scale for measuring how strong the turbulence is. So severe turbulence, this definition of severe turbulence means that it's stronger than gravity. So the plane will be moving up and down with a vertical acceleration that is stronger than 10 meters per second squared, stronger than gravity. So if you're not seatbelted, by definition in this turbulence, you will lift up and hit the roof of the plane. That's the definition of severe turbulence. And there are fatalities caused by turbulence on small planes, private planes, hundreds of serious injuries on commercial aircraft. Can you see anything wrong with that plane in the picture?
One engine on one wing.
Yes, it was flying through turbulence that was so strong that this engine and about 6 feet of the wing just broke off mid-flight. And I'm told that is a design feature. Some of you might know more about this than I do. Yes. It's special shear nuts and bolts that fix the engine to the wing. The last thing you want is an unstable engine kind of hanging off the wing. And I'm told that the fact that it broke off kind of saved the lives, essentially, of the people on board this plane.
Great for the plane, not so good underneath.
Yes, flying over the Rockies, as far as I know, it didn't hit anyone when it landed. Flight diversions and delays and a cost of maybe up to $500 million. Figures are very hard to come by. According to this study, it's the leading cause of airliner accidents. Of course, mechanical failure contributes about 1/6, according to this study, of accidents. So nuts and bolts, like the engine dropping off that plane. Things go wrong. Human factors, pilots do make errors, very rarely, air traffic controllers, about 1/6. And a further 1/6 coming from people dying on board, which this study counted as an accident. But turbulence, as you can see, accounting for about half of the accidents according to this study. Has anyone here never flown before, can I ask? Has everyone in the room taken a plane before? Has anyone never flown through turbulence before? Okay, looks like everyone has, which is when the plane just goes up and down randomly. Sometimes there's one or two people who've never flown for whatever reason, maybe financial reasons or maybe trying to not damage the environment too much. So often some people just don't know what it's like to be in turbulence, and I have to kind of explain it. And the best job I can do is play you a short video from Live at the Apollo, this BBC TV series. The comedian Josh Widdicombe describes what it's like to fly through turbulence. And I can talk in academic terms about what turbulence means in terms of the key root of the eddy dissipation rate being more than 0.5 metres to the 2/3 per second. But just to hear it from Josh Widdicombe, he does a much better job at describing it than I ever could. So here's a short video, just about a minute long. Oops, and I have to click on it, don't I?
I like the train. The train is my preferred method of transport. I don't like flying. It scares me. I don't know how people aren't scared of flying. How are you okay with turbulence? The first time I heard about that, I couldn't believe my ears. So what was that? I was sorry, did I not tell you? Sometimes when you're 5 miles in the air, the plane will go up and down uncontrollably, and there's nothing the pilot can do about it. That's not an acceptable feature. You come on the bus and they might just, so you know, sometimes halfway down the motorway, might just zigzag in and out of lanes. There's nothing the driver can do about it. You're alright with that, aren't you? No. So I'm not a psychopath.
So that's what it's like to fly through turbulence. I'm going to focus, because there are different kinds of turbulence, I'm going to focus on something called clear air turbulence here, which is the hazardous kind, because it's invisible, as its name suggests. If you fly through a cloud, the convection or the rising air inside the cloud will always cause a little bit of turbulence to some extent, but at least the pilot can see that, and the radar on the plane can see it. There's a kind of turbulence that is not detectable by the electronics on board the plane, and it's also invisible to the pilot's eye. This clear air turbulence that happens in the jet stream. And it tends to happen when the seatbelt sign is switched off, there's no visual cue, people will be moving around inside the cabin, and just suddenly, with no warning, the plane will hit a wall of turbulence. Many of you will have experienced this. Although we do have forecasts of it now, and they're getting better, and often the pilot will know that they're about to hit some turbulence, but not always. It's called clear air turbulence, and a convenient acronym for it, of course, is CAT. So in the next few minutes, or in the final few minutes of my talk, I'll be talking about CAT. And just so you don't get too confused, obviously I'm not that kind of CAT. As I say, we do have forecasts, and one of the projects I've worked on is the development of better algorithms for forecasting where this invisible clear air turbulence will be, 6-12 hours ahead. So that pilots, when they take off, will have an idea of where the turbulence might be and can proactively put the seatbelt sign on before they hit the turbulence. So one of the projects I've worked on, which is quite a satisfying project, because it's now being used in aircraft operations. Whenever you board a plane in the US, this algorithm that we developed will potentially have been used to route the plane around the turbulence. And we're pretty good. We're not perfect. It's like a weather forecast. It's not 100% right all of the time, but we have a pretty good idea now where this clear air turbulence will be based on a particular algorithm, even though it's invisible. Well, there's a bit of a suggestion that turbulence might be getting stronger because, according to this chart, more people are being injured by turbulence. In fact, over this time period from 1982, the number of people being injured by turbulence, this is a US Federal Aviation Administration statistic, so it only concerns US carriers, so British Airways is not included in these statistics. It's American Airlines, United, Delta, the American registered airlines. The number of people being injured by turbulence has gone up by a factor of 5 since the early 1980s. Now, most of that growth is due to the fact that more people are flying. So it stands to reason that you'd see more people being injured by turbulence if more people are flying. But this chart has been corrected to strip out that effect. It's the number of serious injuries, including fatalities, caused by turbulence per million flight departures. So the fact that there are more planes in the air is not what's driving this increase in the injury rate. It's approximately doubled over this 20-year period. And it's now about 1 in a million. So for every million planes that take off, there's one fatality or serious injury caused by turbulence. So of course it's quite rare. We think that only less than 1% of the atmosphere contains severe turbulence at any time. So the probability of your plane tomorrow hitting some severe turbulence is almost zero. But multiply that by the number of planes that are in the air, at any time, and sooner or later, and probably sooner, one of those planes will randomly just hit that 0.1% of the atmosphere, or whatever it is, less than 1% of the atmosphere. So I always try to reassure people, because maybe some of you are going to Heathrow tomorrow to take a plane somewhere, I don't know. The probability of your plane hitting severe turbulence and you being one of these statistics is not something that you should be worried about. The old saying, you're more likely to be injured on the way to the airport than you are on the flight itself. But you will see people injured by turbulence, and it's quite a newsworthy event now, because people get their mobile phones out and start filming it, and it tends to go straight up on YouTube and get shared many times. So you will see videos of people, injured, skull fractures, etc., by turbulence. Now, I think I'm slightly running out of time, aren't I? So I might skip over some of these details, except to say that clear air turbulence is caused by instabilities in the jet stream, in simple terms. There's a whole mathematical theory around this. It's called Kelvin-Helmholtz instability, and it's quite an ancient, well-studied instability in fluid dynamics. But I think all you need to know for the purposes of tonight's talk is that there are instabilities in the jet stream, and that's what causes clear air turbulence. And it's all got to do with this thing called shear, which is the fact that the higher up you go in the atmosphere, the faster the jet stream blows. I don't know if you've ever climbed the Eiffel Tower, but when you're at ground level, usually it's not very windy, but the higher up you go, the windier it gets. And that effect continues in the atmosphere all the way up to 30,000 feet. It gets windier and windier. And that increase in the wind speed is called wind shear. And it's the wind shear that causes clear air turbulence to break out. And because the jet stream, as I've shown you, is getting stronger, it follows that the wind shear is getting stronger as well. And we've actually studied this. Actually, you're amongst the first people in the world to see these results, because they're not published yet. They're about to be submitted for publication to a science journal. But we've gone back to the satellite era, the start of the satellite era, which is when satellites started monitoring the jet stream in the late 1970s, to the present day. And we've looked each year at the strength of the shear in the jet stream over the North Atlantic at flight level 350, which is 35,000 feet. And there's been it goes up and down from one year to the next. Without going into detail, we've used two different databases, a European one and an American one, just to check whether this is a robust finding. So it goes up and down from one year to the next. That's not very surprising, but there's clearly in both datasets a long-term upward trend. The shear is getting stronger, and as I've shown you, that's because the jet stream is getting stronger. And an inevitable consequence of that is that clear air turbulence will get stronger as well. So let me tell you in my final few minutes about the study we've done into how turbulence will get stronger in future. We've taken some, as I say, we don't have satellite observations of the future, so we have to use computer models. But the models are so good these days that I could show you satellite and model, and it would be very hard to tell the difference between the two. So here we are looking at two atmospheric models using, without going into detail, a particular mathematical representation of turbulence. So the red colours here mean there's turbulence, essentially. And I'm looking at two simulations, what you can regard loosely as being a 20th century and a late 21st century simulation, very loosely. So the scientific question I'm asking is there any evidence of more turbulence in this world on the right, where the CO2 has gone up, been doubled in fact, and the jet stream has got faster and the wind shear in the jet stream has strengthened? Is there any evidence of any more turbulence? And you can watch these movies and you can try and convince yourself that there's more red patches over the Atlantic here than over here. But the best thing to do is to do the calculations properly, and that's what we've done. So here are our published findings. The different colours here are different models of turbulence. I don't really propose to go into too many technical details, except to say that for light turbulence, which is a slight strain against your seatbelt, no one's ever been injured by light turbulence. But it does worry nervous flyers, and a very large number of people actually turn out to be afraid of flying. I can't remember what there's an international body that lists psychiatric and psychological disorders, and fear of flying is on that list now. It's a recognised, diagnosable psychological condition, fear of flying, and it's very prevalent. The people who don't like flying, you don't tend to meet them because, and they tend to keep quiet about the fact they don't like flying. But it's a very common fear. And light turbulence, although it doesn't injure anyone, it does scare the hell out of nervous flyers. We see an increase of between 40 and about 70% later this century in the amount of that turbulence over the Atlantic. For moderate turbulence, which is a definite strain against seatbelts, but again, no injuries really, we see, well, on average a 94%, but quite a degree of difference between the different calculations, anything from 40 to 120%. But then for severe turbulence, which is the category that does injure people, as I say, it's stronger than gravity, so gravity can't pin you down to your seat strong enough to stop you from becoming a projectile in severe turbulence. You'll be forced violently against your seatbelt if you're wearing one. Objects being tossed about, food service impossible. We see, on average, a 150% increase in the amount of that turbulence by the time carbon dioxide doubles. And it's not entirely clear when that point will come. It depends how much CO2 we keep putting into the atmosphere, of course, but probably later this century. And it's happening, I'll skip over that, I think. It's not just happening in the North Atlantic Ocean. We've done a recent study. My PhD student has led a study looking at different geographic regions, different seasons, different flight levels, different computer models, and we always see the same thing. In the mid-latitudes in both hemispheres, northern and southern, in all seasons, all flight levels, different computer models, we see the same increase of a few 100% in the amount of turbulence around. Concentrated in the mid-latitudes, which happens to be where people tend to live and fly. So this seems to be a very robust finding. Of course, if there's just one scientific study on something, you tend to be a bit iffy about it. It could be anomalous. But when you see the same thing in multiple studies, in multiple models, at different flight levels, different seasons, you start to think that it's a robust result that is not just a random finding that's wrong. I don't know if any of you are on Twitter, but it's quite interesting to look at what people say about you on Twitter when you publish a paper. Here's someone saying that, if turbulence increased, it would definitely make me, almost not fly, or reconsider her flying habits, she says. Here's a frequent flyer who says she flies every week, and turbulence was much higher recently, so that's interesting. Of course, it's just one data point, just one person. It's not a scientific finding, but consistent with what we expect. Do you remember Captain Sullenberger, who landed his plane in the Hudson River a few years ago when it was struck by a bird? He started to tweet about this as well, and fellow airline pilots started to chip in and say he's been mentioning this to his non-aviation friends. He's seen a noticeable difference over the last 5 to 10 years. And finally, Chelsea Clinton started tweeting about my study, which was quite nice, and got us a lot of attention. Do I have a minute or two left, John, or should I stop? Okay, well, this will be my final slide, which is, I don't know how many of you know this guy, but he's probably the world's most famous climate scientist, Michael Mann, who works in the US. He's been the subject of a lot of abuse from people who are sceptical about climate change. But I'm going to play you just a 1 or 2 minute recording of he won an award in the US, I think about a year ago, and gave a lecture as part of the awards ceremony. And he tells a little anecdote here, and I have the audio recording of it, which I'll play back to you, which is when he's boarding a plane and the pilot kind of recognises him, and they start having a conversation about turbulence and climate change.
Michael Mann, speaking of weather, you were boarding a plane one time and the pilot asked to speak to you. Tell us that.
That's right. I thought he was in trouble.
Not because you were drunk and disorderly. No, he was probably just on the plane.
No, it was the flight attendant came back and asked me, "Are you Michael Mann?" And I didn't know if I should answer yes or no. And the pilot had recognized me and wanted to talk with me. And in fact, he was convinced that he has seen the impact of climate change on aviation, on turbulence in the atmosphere. And he was quite informed. It turns out that he follows the climate literature and the blogs, and he sort of knew what he was talking about. And he was absolutely convinced that he is seeing changes in sort of turbulence that are unusual in his career and that he thinks are a manifestation of climate change. And it's consistent with what we expect. We do expect more turbulent energy in the atmosphere as it warms up. To me, that really drove home not just the fact that I have to be careful what I do and say, because people do actually recognize me now and then, but it really conveyed to me in a very profound way the fact that the impacts of climate change are no longer subtle. People are feeling them and seeing them in their daily lives, and I think that's making a huge difference when we try to communicate to the science and its implications to the public. They sort of get it now at a level that I don't think they did in the past.
So to summarise, your flight's going to get bumpier. In addition to all of the other impacts about sea level rise, possibly flooding your airport before you even get there, your plane having problems taking off, more lightning strikes of planes, journeys taking longer as the jet stream speeds up, more turbulence as well, with the statistics that I've shown you about, maybe up to a 149% increase in the amount of severe turbulence which injures people. So I think we'll see bumpier flights later this century, and one can speculate what consequences that will have on aircraft operations. If there's twice as many patches of turbulence over the Atlantic, it's less likely that you'll be able to go in a straight line or on the flight route that you want to go on, as calculated by those equations. It's twice as likely that there'll be some severe turbulence somewhere along that route, and you'll have to fly around it, and that takes longer, or over it or below it if you can. So I think we might see journey times lengthening just because of the more turbulence problem as well. And it has all sorts of other consequences. Pilots submitting route changes to air traffic controllers increases the workload on air traffic controllers, for example, who have a very difficult job. Possibly increasing fuel consumption as well, and kind of feeding back on potentially increased ticket prices, of course, because someone has to pay for the fuel. Okay, and that's where I'll leave it. I'll be very happy to take questions if anyone has any, but for now, thank you very much for coming and listening to me speak.